Hello and good afternoon. My name is Walter Rustler and I will present this webinar today to you. Today's webinar is about structural analysis of steel structures using RFEM. We will start with modeling a simple model from a framed structure. We will enter some loads and load combinations. We'll then provide an analysis and design according to Eurocode. And at the end, we'll take a look at the printout report. Before we start with the live demonstration, I would like to point out the workflow inside RFEM and RF Steel EC3. RFEM and RF Steel EC3 are the only modules we will take a look at today. So if you're looking for a Eurocode solution, those two programs are the ones that you need. When designing according to a certain code, all the design parameters must be in alignment with the codes. It starts with specific materials, with specific parameters, with specific loads according to the code, with specific combinations to that code. Also, cross-section values can vary from code to code. And at the end, the code itself has several different design parameters. Usually there are several options that you can use, and in case of the Eurocode, we have national annexes we have to take a look at. At the end, it makes your design flexible, and the goal is to have an economic and safe design. So it's vital to have access to all those variable parameters. In the case of RFEM, we have at the beginning the choice to choose a standard for the load cases and combinations. We'll see this in the demonstration. When we talk about materials, we have a material library that can be filtered according to different codes in different countries, and it will then provide the specific parameters for this code. When we talk about the cross-section, there are also special parameters in the cross-section library, for example, in case of Eurocode, shear area according to Eurocode, or buckling curves according to Eurocode. When choosing the design module for Eurocode, it will automatically use those parameters. Same is valid for other design codes that we are using. When we talk about loading, it's clear that different codes and different provisions have different loading patterns and different wind and snow loads, for example. We have powerful generators inside RFEM for those type of loads. In the design module itself, there are many options that we can set up how we do the design, which provisions we will use or not use. We also will take a look at those settings later. And in the case of Eurocode, there is a wide range of national parameters that are different from country to country. The goal is really to have an economic and safe design, and we think it is very important that you can change those parameters and are flexible in the design process, because then you get really the best result and it makes your design very flexible and safe. When we take a look at RF Steel EC3 in detail, it does a cross-section classification, so you can handle compact and slender cross-sections as well. And you can do an ultimate limit state design. You can check for your deflections and do a serviceability limit state design. You have a very powerful option to check against stability for buckling and lateral torsional buckling. Additionally, you can do fire resistant, and you can also use stainless steel in your design process. Some special things about RF Steel EC3 are that we can, for example, choose between a member design and a set of member design. When we model a complex building or some structure with lateral intermediate supports, typically one part that would be built or constructed as one physical member is modeled as several analytical members. So one unity, this integrates into several different parts. So now we can refer the design to the individual members, or we can refer the design to the so-called set of member. So with the use of a set of member, we group again those individual analytical members into one physical construction part. When we think about buckling lengths, slenderness, loading, and also horizontal supports, it's clear that the length of a member is a important parameter for critical loads and critical moments, for example. We also can handle lateral intermediate supports in a very simple way. You don't have to divide members when you want to put a lateral support, for example, with a nodal support there. You can just assign the distance of the lateral intermediate supports in the design module, and when we talk about critical loads, effective lengths, the software will take care of it, and it knows that there are those supports. A very important feature is the lateral rotational restraints and shear panels. For example, if you have a moment frame for a steel hull, and you can take into account the diaphragm that is stabilizing the I-beam against rotation, you can reach much higher critical bending moments, and therefore you get higher critical values and a better design ratio for your stability design. And this is vital in those cases. If you don't have this, the chances that you have to use a larger cross-section are very high. Also, it is important that you have a good, stable numerical solution for your critical forces, namely the critical axial force and the critical bending moment. In the code, there are simple analytical formulas, or mainly in the national annexes, with parameters C1, C2, C3. Those are derived from a simple fork-supported one-bay beam. And in many cases, the results are on the safe side or sometimes even on the unsafe side. Therefore, the code requires, when possible, to use such a numerical solution that can handle the support conditions and the loading conditions much better than those analytical formulas that are only valid for a certain type of support and loading. RFEM includes such a FEM-based analysis inside the module RF Steel EC3, and for any load case, for any loading situation, for any members or set of members, it automatically does this numerical analysis in the background. So you have a very good result for this really important design values for your Eurocode design. It's also important to understand what the software does, and therefore we provide a full listing of all the intermediate results, including a code reference in the module. With this code reference, you can put the code next to your computer and check the formulas and understand exactly what the software has done. You can also make hand calculations and compare what the code gives as a result and what the software gives as a result. Therefore, you can raise the trust into your software and you can prove all the other engineers that look at this design that your calculations are correct. Inside RFSteel EC3, we already have built in some newer research results that may be used in the next edition of the Eurocode. There are some limitations in the general method of EC3, and for example, you cannot use this general method for double bending, which is quite often during the design process, and we have already included those provisions that are published in magazines, in recognized magazines, in RFSteel EC3, so you can already now use what may be the future code solution. Once you have understood how we do the design process in Eurocode, you will be able to apply this knowledge also for AISC, ISGB, which is Chinese code, British standard, Australian code, Swiss code, and Mexican design codes. Everything follows the same red line, everything follows the same design principles, and once you know one module, you most likely can work with the other modules because everything is tailored the same way. That results in a very low learning curve. You don't need any time or less time for training, and you still can get a fast economic design. At the end, if you are new and you're thinking buying the software, it will reduce your cost and it will result in a fast return of your investment. Before we start now with the live demonstration, I'd like to explain a little bit about the webinar software. You see the control panel. You can hide and show it with the red button in this control panel, and you can also ask during the webinar short questions, and my colleague Robert Vogel, he will assist me today with answering those questions. Thank you, Robert, for doing this again, and I ask you please ask short questions. If you have demand for more knowledge, for more detailed problems, please do not hesitate to send us an email to hotline@dlubal.com. We will get back to you as soon as possible. The live demonstration will consist of following. I will do this roof of a gas station inside RFEM. I will model it very quickly. I'll put in a total of, I think, 6 load cases. We'll do combinations and then look at the design module. I'll go through the modeling quite fast because the focus today should be on the design. Nevertheless, I think it's important to see a full from A to O design process inside RFEM and RFSteel EC3. I have already RFEM open, and when you open RFEM the first time, typically you get the new model generate data dialog. Here I enter the model name, and I can enter here model of gas station. It can be also some kind of number, project number, whatever you want to use. In this dialog, we have here the setting that we can choose create combinations automatically, and then we have to choose a code. We have several codes in here, and all the design codes that we have also come with this automatic setting or choice of code for the automatic generation of load combinations. We'll choose here Eurocode in this case, and since we have an international audience today, I don't want to prefer any country, so I stay with the general European Union default settings for the national annexes. I can view those settings referring to the combinations, and you find here exactly the words as they are in the code and the parameters that are the default parameters. If you want to change it, you can go ahead and create a copy of this standard and apply your own factors. Okay, when I press OK, there will be a new workspace that opens. I have my set of navigators at the left, data, display, and views. Later there will be results. I have my tables here on the bottom that I can use for input, and I have my graphical workspace. Before we start, I like to open or to enter a few cross sections that I would like to use for this presentation. For the steel posts, I'd like to use a wide flange I-beam or I cross section, and I'll choose a HEB 300 at the beginning. My material is already set up to steel, and I can show you also here the library, and here you have the filters, first for the material and then for the standard groups that are available here. In any case, it's possible also to have a favorite group where you can just set up your own choice of materials. On OK, the cross-section is put into my file. Next, the cross-section for the cantilevering primary structure of the roof will be an IPE 400 made also from steel. The third cross-section will be for the purlins, which is again an IPE cross-section size. Let's start with a 300. And I have another cross-section I like to use for the edge of the roof, which will be a channel section size 200. Everything made from steel. Okay, I do this. You don't have to do it that way. I do it because then later on I can just select those cross sections easily when I set my members. To set the members, I work with my grid, which is set up to 1 meter spacing. You are not bound to that grid. You can change to any coordinate if you want to. It just helps me to model it very quickly. There are other ways also how to import structures from CAD applications. We can use background layers that we can snap to and different ways. But I'll do a free modeling today, and I start with my first column, which will be an HEB 300. Member type is beam, and I'll just click OK, and I start from 3 meters from the origin, and the length and the height should be 5 meters in the vertical direction. My first post is there. I see it's not oriented the right way. I rotate it by 90 degrees. Now I want to model the cantilevers. So I'll put the origin of the grid on top of the column, I use the horizontal grid outline and enter my next member. And here now I can simply select from my choice of cross sections that I've done before. So the length should be 4 meters. If I hover over the section, I see the length at the popping up bubble at the end. Same thing on the other side. I do again the same procedure, and I have here my first T of my roof. I'll put in here now another support. I'll use a nodal support, which should be rigid or fixed in this case. Next, I'll make a copy of this 1T to the other side. I can move my origin of the grid again to the bottom. I hover over the selection, press the left mouse key and the control key, and create a copy in the distance of 6 meters. Sorry, I didn't press the control key. Select, control, wait a little bit, copy, 1, 2, 3, and here we have a copy. Okay, quickly I will proceed in modeling the purlins. I start from right to left, new member, new cross section, and we start from here to here, from here to here, and from here to here. So there are 3 members. I select them. I'll create quickly 8 copies with a displacement vector from here to here, -1 meters. On OK, everything will be copied. So we quickly created this grid type for the purlins. At the edge, I will put another cross section. This time I'll use a channel, and I'll enter it from both end nodes. We'll check the rotation, and we'll notice that we have to rotate this last channel by 180 degrees. Okay, now we are basically done with the main model. What is missing is some releases. Everything is now rigidly connected. Even here, where I have no intermediate division of the cantilever beams with the purlins, it will be still possible to analyze it, because RFEM automatically realizes here is a node that is on the center line of this primary steel structure that we want to connect. You can set this up in the calculation FE mesh settings, and here is a check where we can use this division of members that is done in the background. Here's the setting. Same is valid for the edge beams here with the channels. Okay, we'll quickly check whether we have the right cross section. So I can go to the table here and just flip through the lines, and we'll see there is a highlighting of the selection. When I select it in the table, it will be highlighted in the graphical work window. If I don't want to see those tables, I can hide them. Okay, I said we were going to enter some more releases. I'll create in my data tree a new release. You see here, everything that I have done here is also inside the data tree, and I can create a new member release or line releases and so on. There's different values, there's different ways how to do this. Member end releases, right mouse click, new member end release. I want to have the situation that these purlins will cross the primary steel structure but transfer no moments. So it will be really a crossing of two beams, and they act like a scissor. That's why it's called scissor type. So to have a scissor type release, I'll have to choose a global release as scissors, and the scissors will be about the global y-axis and z-axis. Moments, which would be torsional moments, should be transferred to the primary steel structure. I need this setting so I don't have a kinematic system. Okay. Once I have this release defined, I can assign it graphically to the members. If I want to have it on both sides, I select the center part. If I want to have it just on one side, I can select the one side, either individually or with a window. Yeah? But you have to make sure you don't select everything else which is wrong. And I did this now here, so I have to deselect it again. Okay, one more time. Once, and then we'll do this here. Okay. Well, you see it's a live demonstration, and not everything always goes the way you want it, but I hope you understand how those things work here. Okay, here we go. Now we have the scissor type on both beams, and at the end I want to have a regular release, and I create a new member end release, and this time it's a local one, and because I want to hinder the channel from rotating about its own axis, I put here a small spring around the local phi y-axis. You see here the coordinate system, and now I can do also following. You see here when I hover over it, there's a little arrow, so the end is on the outside here, so I select those members, double click on it, and releases at member end is the local one. Okay, and here it's the member beginning, double click, and there is also the local one. So within a few mouse clicks we have assigned those releases. We can save during the work with the software, and next we'll be working with the loading. I'll show my tables again, and I display the load cases combination tables. I start with entering the load cases. This time I have 6 load cases. First one will be self-weight. It automatically finds that it is a permanent action. It automatically knows we most likely want to have the self-weight of the model structure activated. Next will be snow, which is snow load, no self-weight activated. Then we have 2 wind load situation, one in plus X and one in minus Y. And we have also the imperfection in X direction towards X and the imperfection towards minus Y. So there are 2 imperfection load cases that I want to apply, because if I do a second order analysis including imperfections, I'll will not have to deal with buckling lengths and critical lengths inside the steel EC3 module. There is a provision in Eurocode that in this case the regular length, which I modeled here, is used as the buckling length and can be used as the buckling length. Okay, I have actions, so I have two wind loads which are automatically recognized as alternatively. So wind in one direction cannot be at the same time with wind in the other direction. So we have now three actions basically, and the combinations that the design situations I want to take into account are the ultimate limit design and the serviceability limit design situation. In this case, I'll only want to do the characteristic design situation because it is the one that is controlling in that case. And if you're not sure, you can do all the combinations, of course. And I also want to consider imperfections. When I check this consideration of imperfections, I'll have several other options. For example, I want to avoid that there are load cases or combinations with and without imperfection. I always want to apply imperfection. And I also want to avoid that there are imperfections in both directions at one column, for example. So those two checks have to be set if I want to do this. Then subject to specific load cases, I also want to check. In this case, I can reduce the number of combinations if I say, okay, wind towards X should never be applied when there is wind in Y direction. And in the same way, imperfection towards minus Y should not be applied if there is wind in X direction. If I use common sense, I can figure out which load cases or load case combinations are most likely the one that control, and I don't have to analyze an immense amount of combinations. If you don't want to use it, you can forget about it and just do all combinations, but it will result in longer calculation time and more data to analyze and so on. Once I have set this, I go to the next table, action combinations. So now it will show me the combination string or the combination criterion based on actions. So there's only wind with factor 1.5, and it includes their load case 3 and 4. This is a more simplified representation of the combinations, and the real combinations are then in the next table, where you can see that we have now 10 ultimate limit state combinations with factors, and we have also 10 serviceability limit state combinations with the corresponding factors. Every time I change something, RFEM will update all those combinations because I checked automatic generation. In the result combinations, I get the envelope result of all ultimate limit state or serviceability limit state combinations. Okay, next we'll have to enter some loads, and I'll have to speed up a little bit so we get ready within the right time. I'll change the view to the wireframe view, and while I do this, I noticed I have here made a small mistake. I see there is also a release here. To avoid any complications, I'll just set this to none and change it. So now everything should be fine. I'll set up the first load case, and we'll create a member load via area load of size 0.5 kilonewton per square meter. I have to assign the impact area of that load. Okay, okay, okay again, and I'll see here the first load case. Second load case will be snow. I can just leave it as this, but in case the roof would not be horizontal, you could set up different projection patterns and so on, and the snow load should be 1 kilonewton per square meter. It remembers the setup of the boundary for the area. I just need to change the load size, magnitude, and I get this second load case. Third load case will be wind in X direction. Before I do this, I have to do something else I want to point out. This time I will have a pressure load on the left side of the roof and a uplift load on the right side of the roof. So I will have to apply the load only on part of these members. In order to be able to do this, I can create some helping nodes, which I will do now, which will be in the center of those boundary members. Now I can use those nodes to define my area for the area load. So the compression should be 0.1 kilonewton per square meter, and I can snap to this center point. Here we go. Okay. Okay. If I want to show the real load pattern, I can show it, and you see it ends here at the center, and it's distributed trapezoidal where several members intersect. On the other side, I will do an uplift. So there is minus 0.25. I'll delete the impact area and set it up new. Okay, okay, okay. First wind load case. Next wind load case, wind from minus y. Same thing again. I start with the uplift load this time. And I don't need the helping node in this case. Okay, okay. And one more time, the other half of the roof. Okay. Here we go. Last two load cases are the imperfections. I'll be able to display the local axis of the members. In the display tree here, you have all those settings, and you can see the local axis. Also in the view tree, you can show only certain members, for example, only the columns, and then I have only those members active that I want to work with. This time I will apply a imperfection towards X, new imperfection. I can apply them according to local axis. This is why I showed the local axis. This time I will have to have the local axis Y, which is taken into account. I want to have the inclination in positive direction and the precambering into negative direction. I can choose here the values for the imperfection. I'll even have the option to use some formulas from Eurocode to take into consideration several columns and so on, but you are able to enter it freely yourself. So those values are kind of on the safe side. I'll work with those at the moment. Okay, and then I'll just enter it just like any other load. Next load case will be in the other direction. This time it should be in local axis C, and pre-cambering should be also this way. So here we go. Now we are done with the entering of our model and the loads, and we can proceed with the analysis. I can run the analysis and I can say calculate all. We'll do a second order analysis of the load combinations. By default, you can of course use a first order analysis or a large deflection analysis. Everything can be set up in the calculation parameters. In the little displacement diagram here, you see how the iteration process is done, whether there are maybe situations where the software doesn't converge, where there is no converging result. Yes. Once we are done with our analysis, I can go back and switch off my member access system, and I don't want to see the loads, but I want to see the deformations. Everything seems to be, this is now self-weight, seems to be symmetrically, so I think we did everything okay. Let's check the bending moment quickly, see what happens here. My, MC, here we go. And we see here, we have here a typical bending moment diagram. We see here also where we have the scissors force releases, that there is a bending moment, there is a bending moment, and there is no torsion involved in this main principal axis, principal steel structure. So it's really a scissor type hinge. We have a minor, very small torsional moment due to this connection here, which we can really neglect. And it seems to be symmetrically, so everything seems to be all right. We have axial forces, so everything seems to be reasonable. We can navigate through all the combinations and do the same thing here. Maybe go back to the bending moment, which is maybe the most interesting part. Sometimes we should also have some bending in the weak axis and so on. Okay. Next will be design. We start with going to the data navigator and we'll take a look at the design modules. Now everything we saw now here was plain pure RFEM. When we talk about steel Eurocode design, we need the module RF Steel EC3. We open it by double-clicking on it, and now we'll have everything that we have in RFEM available in this module. Since all members are also modeled in the basically design lengths or effective lengths that we will use, I can check here all members for design. So it will load all members for design in here. I also want to do a design for the ultimate limit state, so I can use the result combination, which is the envelope selected for design. Again, I use the national annex or the default parameters for the national annex. Serviceability limit design and fire resistant design. I will talk about serviceability limit design later. Fire resistant design we leave out for the moment. We go to the next table, materials, and we see our material parameters. Note that you have different yield strengths for the different thickness of the local parts of the cross section. So it's also very important to take this into consideration. Cross sections. We see the list of cross sections. I can do an optimization. I can choose from current row, which will choose the best fitting HEB section, the best fitting IPE section, and again the best fitting IPE section. And I can do this also for the channel section. I have all the parameters here. I see, for example, I have a share area which is according to Eurocode, and I see the chapter of the Eurocode here. Lateral intermediate supports, we leave them out for now. Effective lengths, you can enter critical values, buckling lengths, and you have the option to take into account warping when you talk about lateral torsional and torsional flexural buckling. So here you have options to consider warping, restraint on one end, on the other end, partially, and so on. Since I modeled it with system length equals design length, I don't have to do anything here. Here you also have the option to load some default typical settings which are known from the literature, or you can also import values from the additional module Serviceability, which allows you to analyze a critical load or buckling length. The parameters for members allow you to take into account shear panels and rotational restraints, especially, for example, from a steel deck. Also for tension forces, you can reduce the cross-sectional area to a net area, for example, to take into account bolts. Okay, we take a look at the details, which are common for all national annexes. We have here several registers where we can change different settings. I'd like to point out the stability settings. Here we have the option automatically by eigenvalue method determination of elastic critical moment for LTB, lateral torsional buckling. So this is the very powerful numerical solver that sits behind each member when we do the analysis. You can choose here, for example, whether you want to use the general method or the equivalent member method for the sets of members. We might have to take a look at it later. Okay, serviceability, you have various settings. I think I'll leave it out now. We could talk several hours about it. Fire resistant settings and other settings, for example, regarding slenderness. When we talk about the national annexes, we have access to all the safety factors. We have the limiting deflection relationships. We have here the option to use, for example, this result of the new research that has been done for the general method that I've mentioned at the beginning. Another important feature of RF Steel EC3 is that we automatically determine which equation, there can be several equations, but we determine automatically which equation is the most economic. So you can have a conservative method by equation 656, or you can use a more economic equation, but it's only possible for rolled sections, under equation 657. And we've encountered that sometimes the one or the other equation is a little bit more economic. So we take a look at both results and take the most favorable. Then we have the interaction factors that are chosen automatically according to a certain method. Some sections are of type I, but maybe there's just a little plate welded on one flange, and then in general you could say it's not an I section anymore, but we still want to treat it like an I section. So we have a check here to allow this, for example. And also you have the options for the national parameters for stainless steel. Okay, we run the analysis. We get now the optimized results. In RFEM 5, RF Steel EC3 was increased in speed. It's much faster now. It used to be in previous versions. We have here now optimum result of 99%. We see here design by load case, and we see here the highest design ratio is at member 20 at location 6 meters. If I pull it down, I should be able to see where it is. Maybe we'll go back to here. And I'm not sure, but maybe there is a problem with the software where the audience, where you do not hear me anymore. I don't know what happened. It seems to be all right. My colleague just signals me it's fine. I'm sorry for these problems. I hope it will be okay in the recording, and I hope it's okay. So we see here all the design details from the material values, from the cross-sectional values, from the design internal forces. We see here also the classification of the cross-section. This time we have class 1. And we see here all the intermediate values. We have here the reference to the tables in the code, and you can check it in detail if you want to. We go on with the design ratio, all the input parameters, and down the line at the bottom you have the design ratio, the final design ratio. Everything is commented with the reference to the codes. If we have design by cross-section, we'll see also which check is controlling and which checks are done. We see here the stability analysis, for example, flexural buckling about C-axis. We can also check the details here, and we can do the same sorted by members. If I'm not sure where the result is, let's go to the graphics. I want to return to Steel EC3. Start it. So when I'm not sure where it is, you can navigate through your result table and you will see, for example, I want to know this member here. You will see where we are. It's section number 3, member number 20, member number 21. You see where the design results are from. Okay, you can check this also graphically. If I want to look at the results, I get my result panel here, and I have a nice graphical representation of the results. I can change the view, the display of the results here in the display navigator and check here cross sections, for example. Now we see exactly where we have the highest design ratio. Yeah, or you can do it without diagram, then you write here the numbers, which is a nice way to make a documentation. I'll go back to Steel EC3 because I want to see which cross sections have been used now. So we see here, we have here, originally we had a 300, now we have 160. Here we have a 360, here we have a 200, and we have a channel 160. We do a nonlinear analysis, so stiffness has an effect. Now we have analyzed the internal forces with different cross sections, but I have to update them to get the real effect of the nonlinearity and to get maybe effect of different self-weight and so on. So I export all cross-section to RFEM and do another design round. I run the calculation, and inside the module automatically the needed results are calculated. There can be now instability because we have a nonlinear problem. In this case, I think it's quite okay. We analyzed the cross-section, the optimized cross-section linearly, but we did a nonlinear analysis, so there are some things that are not quite linear, so here we have maybe to do another design round. I have not taken care of the serviceability and the deflections. So therefore, and I know in these cases we have a problem with deflections, because the columns, if they are weak, the whole roof will kind of wiggle back and forth. So I have to optimize one more time this cross section, and most likely I have to even choose a higher, also controlling is the serviceability, and for this probably I have to use even a bigger cross section. And I have done this before, this analysis, and I know I will have to use something like, or we can check it maybe. I enable now the serviceability limit state, and I use my characteristic combination. When I do serviceability, there are additional parameters that have to be set. Let's run it, and the program will, the serviceability data, I have to set which members I want to check. I say members, and I choose my 4 cantilevers from the primary structure, and maybe I choose one of these edge structures, edge members. I can use all of them. I'll just like to point out what's possible here. My 4 cantilevers are of type cantilever, and I modeled them from the inside out, so I want to know the deflection at the free end. So I check here free end. And from the other members, 1, 2, 3, 4, and from the other member, this one, I modeled it from right to left. I'll also use the free end at the end. So it's a difference if you have a cantilever situation or whether you have a beam situation where the maximum deflection will be maybe in between the two nodes, and in the cantilever problem it will be at one end. Okay, and we run the analysis again. So now we need to analyze the other combinations which I didn't run before with the newer cross sections. And then we do the analysis of deflection, and we'll see already, which I kind of knew already, that we have a problem with serviceability, especially here. And this is due to the weak stiffness of the main posts. From the ultimate limit state view, it would be okay. Okay, to make it a little bit faster, I'll choose here now a little bit bigger cross section, HEP 240, and also if I make the cantilevers a little bit stiffer, it also will help. So I use 400 here. So you have the option to set up your whatever you want here. You don't have to take what the software provides for you. I export all those changes, and I run the analysis one more time, and then I should have the correct result. Okay. At the end, I'd like to take a look at the printout report and show you how to do a short documentation of the results. Okay, we have a little bit of problem here yet. At this end, don't worry about it, it's only like 8%, and we'll say, okay, let's not consider this little extra deflection here. Okay, I'd like to do some documentation in the printout report. How to do this? First of all, I'll open a new printout report, again in the Data Navigator. I can select from a template I've already provided inside RFEM, and I click on OK. When I do this, the printout report opens, and I get a preview of all the chapters in the left navigation tree, and I get a nice preview on the right. So I can just scroll through all my results and I can zoom in and I see all the tables, how the results are presented. Next, I will do I close the printout report and I'll print in some graphics. So I had this nice graphic here from Steel EC3. Maybe I like this. Here is my updated view with my maximum design ratio of 74%. I don't like the colors. I can change it. I can go here 74% yellow is not so nice. Maybe I just want to change this to orange and this one also to orange. You can set it up as you like. So between 50 and 80% we have one color. I can give it a name, my colors, and I'll have a better color, for example. Okay, this is a nice picture. I'll print it to the printout report. D1, I don't want to show the printout report, I have the header. I will use 50% of the page. Okay, it's sent to the printout report, I'm done. Maybe I only want to see the results for the cross-section design. I'll do the same thing here. Or maybe for the stability design. So you see exactly what is the problem. Or maybe I want to do the deformation design. So you see, okay, here we have a little problem at the edge. Print that as well. Or you want to have everything. Next, I'll do similar things with my internal forces. I will have to document them as well. I go to a two-color display. I select maybe one combination. Maybe I want to see the bending moments. Okay, something like this, a little bit higher diagram. Looks great. Now I print everything of this. Oh, maybe I don't like the numbers here. I can go to the views and say only my columns and my main girders, maybe the boundary. Okay, looks good. Print. I do a mass print this time. That means I can print this view that I have here of selected or all load combinations. I want to use the ultimate limit state. Okay. Of the internal forces. All 6 of them, of the actual view. Okay. Okay again. And it will automatically process those graphics in the back. Next, I'll do the purlins alone. Something like this. Looks good as well. Print. Same thing again, mass print, results, selected, ultimate limit state, okay, okay, okay. And one last combination, maybe the characteristic results, and I want to see here the deformations. I would like to do a few which has a little bit more impression, a little bit more impressive view. Deformation, members, cross-section colored. Looks nice. Maybe I want to have all the results here. Something like this. Print, window filling, exactly this picture. Okay. Here we go. One last picture maybe yet is with some dimensions. I can quickly put here some dimension lines. Maybe I want to dimension also the distance of the foot points. The height and also the length of the width of the roof. Maybe I'll change this a little bit so I have no overlapping. Something like this. Yeah? Okay, and here I want to use the rendered view, and I print this view to the printout report. And now I'm done, and I want to show the printout report. So on OK, it will take now some time to load the printout report. We've created an immense amount of graphics, and it takes some time to load it. So therefore, it has to update and to read all those results. And we don't want to do this all the time. So we take some time and not open the protocol unnecessarily. But now we see already the result. We have here the steel design results, the individual graphics that we did. We had here the results by load case, by members, member parameters, everything is here. We have a total of 38 pages, which is quite reasonable. We have here the parameters of the national annex that we can look at. We can also go to view, just fit to page, fit 100%, or fit zoom, fit to page, one page. We can take a look at our internal forces. Or maybe I want this picture to be on one start side, so start with new page. So we'll now update everything and move everything, and we'll have a new page here starting with this picture. So it starts on the next page. So we have now two images all the time on one page. So it's nice, and automatically all the graphics are here. You have various filter options in the printout report according to your modules, and you can filter what you want to have here. Maybe you don't want to have the fire resistance data because the input data, because we don't do it. We can deselect it and so on. Also, the cover, I didn't like how it looked like. I can edit it. I go back into the printout report, change my view to the main program, change my view, disable the grid, go back. So it will automatically update the view in here. Okay, once I'm done, I'll close the printout report. I can export it to a PDF if I want to. I'll exit the printout report and I save it. Okay. Now I'm actually done with my live presentation, and I want to look at some questions that have been presented during the webinar, and I'll take a look quickly at the questions, and then we'll see what I can answer now. Okay. Yeah, one question was about this set of member and supports in set of members, and also supports, intermediate supports. So let's go back to this example. When I take here this cantilever beam, and I want to have taken into account the intermediate support by the purlins here, I can edit it. Actually, I have to go to the module, I'm sorry. I open the module, and I edit this, the design parameters, or the lateral intermediate support for this beam here. I can select it, it's number 2. I say here is a lateral support. And actually, it puts here now the option to have a fork support, but I have 1, 2, 3 intermediate supports. So I put here 3. So it's spaced evenly now. If I want to, I can space it relatively or absolutely, and I can change these distances as I want. Okay, I have a fork support. I can choose whether I have a support on the upper or the lower flange, or I can even say user defined, and then I can enter my own distance on which level of the depth of this section I want to have that support. Let's have a fork support for this one, and then we will see the difference on the other side. So we run the analysis again. We see here we have to look maybe at the design ratio of this member in comparison to the other ones. So I go to the graphic, I select the results for steel EC3, and I'll check stability, deformations maybe I don't need. And this time I only view my IPE 400. Maybe I choose the wireframe so I can see everything. So we have the same situation here. Everything is symmetric. We have 57%, and here we have 58 and 52. So we gained approximately 6% effectivity by having this fork support here. If I go back to the steel module and check out the critical loads, cross-section by member, we pick the member, this one, and we see here serviceability, stability analysis, lateral torsional buckling. M critical is 5,373. When I take a look to this other member, which is similar, we have lateral torsional buckling, we have only 422, so about more than 10 times less. So it makes a real big difference. I can maybe redo this and check again calculation of, check again the result of the calculation of this member number 2. Let's pick it, this one. Lateral torsional buckling. So now we're back to 422. So it makes a real big difference whether you have an intermediate support or not. Very powerful feature. This time stability wasn't quite so dominant, but if you have stability as the controlling design situation, it will save you tremendously. The next question, or maybe that's also, there's another question that says, what about those set of members and how that works? How I'm doing this. I can show you this in another model. I have a similar situation here where I have two models, one which is the intermediate beams, and one has the same model with the same loading with the set of member. And if we go to the design of steel EC3 and we select this one, those 6 intermediate beams or divided beams and the lateral, the set of member, and we run the analysis with default settings. Maybe one thing I have to point out, when we have a set of member, we have other support conditions that we can apply, because we use for the set of members by default the general method, and in the general method Eurocode says it can be for any support condition. So we have the option here to set the support, the rotation of the support, the lateral support individually. We can also set the warping restraint and eccentricity. So by default we model a fork support. So now we have one time individuals members with fork support and one time set of member with fork support. And we run the analysis and we get a maximum utilization ratio just above 1. If I look at the graphics and I see here, because we have a longer free lengths for lateral torsional buckling, stability is a problem. Here we have relatively low design ratios. once. So I can check cross-section, stability. So stability is the problem here. Cross-section would be okay, but stability is the problem. So I'll go back to the module, and I change this. Now I model the fork support also at the other nodes here, which will then be similar to what we see on the left side. I click OK. By default, it sets up fork support. Now we have local UI and local VX support. We run the calculation again, and the result should be more or less similar. We have already only 32%, and we see it's pretty much the same problem. So it is vital what kind of support condition you have, and you can do a set of member design or an individual member design. Okay, let me see if there are some more questions that I can answer. Okay. One question was about, what is it, templates. Is the program integrated model templates at example multi-span beams? Templates, maybe there are several templates we can talk about. Yeah? You can have a template which is in the which can use as the block manager. So we have a set of parameterized structures that can be loaded into the same model. It's going with the block manager, and the block manager comes already with a large number of structures that can be loaded inside RFEM. So there is all kinds of whatever, one-bay frames, arced beams, what we have here, three-bay frames, stuff like this, flat trusses. You know, we have, for example, many of these trusses that we can use, and those trusses all are parametric. So if I open it, I'll have a parametric representation, and I can change the height or the width or other parameters, radius, for example, or some are depending from each other. So things can be done with parametric input. Once you have this, you can add this structure to an existing model. So this is one template that we have. This would need another half hour to explain, I think. Then we have templates that we can load in, as I showed at the beginning, in the general parameters, or actually you cannot edit it, that's why it's missing here. But if I create a new structure, you can open a template. You can set up your model that you have with all the cross sections, with all the combinations, load cases, materials, and so on. Save it as template. File, save as template. And once you have this template, you can select it when you open the next model as a template. Okay. One more question was, let me look. One question was about where is the load application. In the Eurocode module, in the details, actually under stability, you can select load application of positive transverse loads. So if you have a transverse load, it will always be applied on cross-section edge directed to the shear center. So it's the destabilizing effect in the shear center, or it can be on the bottom, so it will be stabilizing. So by default, we use the most unfavorable location along the cross-section. Somebody asked, is it possible to do only an elastic design? Because in some cases, I only want to do an elastic design and not a plastic design, especially for if you have to deal with fatigue design situations. Yes, I think it's possible. Yes, ultimate limit state, options, elastic design, also for class 1 and class 2. So when we have class 3, we automatically go to an elastic design. If we go to class 1 or 2, the software will choose by default a plastic design as well, which is more economic. But if you can't use it, you can say here elastic design also for class 1 and class 2, and it will never use the plastic reserves. Another question was, what is the limitations of the cross sections? We are dealing with all cross sections which are handled in Eurocode 3, especially when we talk about stability design. There are not all cross sections for all load applications or design situations. If you have, for example, some I-beams or I-cross sections are tackled really well, and you can analyze them for bending about major and minor axes, including axial force. If you have a angle, for example, then there is no solution for lateral torsional buckling with two directions of bending moments. So in that case, Eurocode doesn't provide, the equivalent member method in Eurocode doesn't provide a solution for it. In that case, you can use our other module, FELTB, which can do an elastic design for any cross-section according to theory second order. Or in many cases, you don't even have to take into account stability. You can just go to stability and say, I don't want to use the stability checks. We do only a cross-section check with check of capacity, either plastic or elastic. Okay, I think this is a lot we learned today about RF Steel EC3 and RFEM. At the end, I'd like to go back to the presentation and point out a few more things. You find a lot of information on our website, w.dlubal.com, including videos, newsletters, and the Dlubal blog. And also you can find download options for test and trial versions. If you go to download, you can download your trial version of RFEM for free. It runs for 30 days. And you can do all the calculations without limitations with all modules. Only in the printout report there is a watermark. I recommend to take a look at the page Help for Beginners. If you open it, this one, you will find introductory examples and tutorials for RSTOP and RFEM. RSTOP works the same way as we just seen in RFEM, but the limitation is it's only for frameworks. In RFEM, we can add on, if you want to, also slabs, volumes, and surfaces if you want to. So, but in general, RSTOP is the smaller brother of RFEM, and works the same way. But you find here on this page for beginners introductory example of RFEM, a tutorial of RFEM, and the same for RSTOP. And also we have several other webinars that we already have done that you can also review on this website. So if you go to the webinar page, here you can sign up for the other webinars that are coming up, or you can view the latest other webinars which are here, and you can watch them. Just log on as you did for this webinar and you will be able to view the past webinars. The new webinar from today will be up online probably by tomorrow, and you will get a reminding email. You're allowed, or you're welcome to come back anytime you like to watch the webinar. The next webinar will be on August 29th, and it will be about RFEM and special features to be more competitive. In this webinar, I will show a collection of what I think good features that save you time, that make you work fast, that make you work productive. I would be very happy if I could see one of or a few of you back again on August 29th. I hope this webinar today was a good invested time for you. Thank you for joining us. Thank you for Robert to answering all the other questions. Goodbye and have a good day.